No, ma'am.
Dear students, a very good afternoon to all of you, and I welcome you to this session of information security. So today we will be starting with the stream cipher technique, which was left that day. That is one-time pad. One-time pad. So in this technique, XOR is applied. Actually, your text is converted into the sky codes. This was developed by Gilbert Burnham in 1918. This one-time scheme was developed by Gilbert Burnham in 1918, and it represents the string as sequence of zeros and one, but in form of a sky code. But in form of a sky code. So, for example, if I take if as a message, plain text, I'm assuming if as plain text, if. So the code for it is see the plain text is IFF, and corresponding to I we have this 7-bit code in the form of 0 and 1, and for F we have code this 1000 1110. So this is your again a sky code for F, right? Now you have been given the key to encrypt it. What you will do, perform the XOR. So this would be the 7-bit key. This would be the 7-bit again. This is your ciphertext. This is your ciphertext for the given message. First of all, IFF, if for that we have converted I and F into the respective sky code that you can see from the various sources. And then we have key which is given to us. Then we have the key which is given to us as 101 0110 0110 001. Just do the XORing of key and the plain text, you will get the corresponding ciphertext here. Next is your transposition ciphers. Next is transposition ciphers. Next is transposition cipher technique. In this transposition, I mean only rearrangement of the letters is being done. No substitution is done here. No substitution is done here. That is, no replacement of characters done, only the characters are merely rearranged. So first technique is rail fence technique. In this, any message is given to us, all the best for the exam. Suppose this is a message which is given to us, all the best for the exam. So you will write this message diagonally, A, L, then write L, then T, then H, then E, then B, then E, then S, then T, then F, then O, then R, then you have E, then you have X, then you have A, then you have M. Fine. So you will write the text diagonally. Just write the text diagonally and read this text. Write this text diagonally and read this text row wise. Read this text row wise. So it is right here. A L H B S F R X M. This would be a first row, and then write second row L T E E T O E and A. So if I write this text completely here, it will be A L H B S F R X M, then L T E E T O E A. So this is the cipher text which will be getting using the rail fence technique. That is, you have to write the text in the form of this. If I write S here, then we may find S and we will get S here. Fine. So A L L T H E B E S T F O R E X A M S, and just read them in a single row. So this would be the equivalent ciphertext of the given plain text. This is called transposition because you will see we have not applied anything here, just we are rearranging the letters in the diagonal form and reading them in the sequential form. That is what we are doing in rail fence technique. Next is transpositions, row transposition cipher. So next technique is row transposition cipher. So in this technique, what we have is, this is a standard formula which is usually used. I tell you how to use it. If some message is there, postpone, attack, till 2 a.m. This is a plain text which is given to us. We have to form the transposition cipher. So write post, phone, just substitute them column wise. Attack till 2 a.m. Now, what we will be doing, whenever you have some dummy bits, write down X, Y, Z, then X, Y. So this is how it is being done. So what we are supposed to, now we are we will be reading this text in this manner. 1, 2, 3, 4, 5, 6, 7. That means it first column will come T T L Y, then second S T L X, then second column is T T L Y, then third column is O A I M, then fourth is P E T A, then fifth column is P A T Z, then sixth column is O C W X, then N K O Y. This is the equivalent row transposition ciphertext for the given plain text postpone attack till 2 a.m. So we will write like this 4, 5, 4, 3, 1, 2, 5, 6, 7. Then you will read it in the column wise manner 1, 2, 3, 4, 5, 6, 7. In the serial order, you are going to read it, but read it column wise and write it row wise. So STLX, write down this way, then TTLY. This is called single transposition. This is called single transposition cipher, where the rearrangement is done using the columns and the columns are read in the sequential manner. This is how it is being done. Okay. You can further okay. Now let's do the double transposition. In this, for example, messages this attack X at dawn X. Fine. Now what you will do is you will write the column C1, C2, C3. Attack X at DAW. Yeah. First of all, step number 1, insert X after each word. In double transposition, you have to insert X after each word. Then attack X at X dawn. Then closing, if some dummy bits we have to insert, we usually do it with X, Y, Z. So I have substituted one X here. And so this is the first thing. Then you will take the column 1, 2, 3 and substitute these values as this thing. First of all, A, T, T, A, C, K, X, A, T, X, D, A, and W, N, X. So this will be complete, metrics for this attack X at X dawn. Fine. Now you are going to arrange these letter. First of all, permute the column as permute or rearrange the column as 3, 1, 2. 3, 1, 2. So if I'm going to rearrange it, so this will be C3, P, K, T, A, X. This is how it will be rearranged because I have brought C3 in front and C1, C2 this way. So this is R1, R2, R3, R4, and R5. So this is my transposition which is done on the column side. Now for the row side, what I will do this way. 3, 5, 1, 4, 2. Column is 3, 1, 2. Then row is 3, 5, 1, 4, 2. So let's do this. This is column transposition. This is your row wise. Three, 5, 1, 4, 2. C3, C1, C2. So R3 would be TXA. Then 5 would be XWN. Then one number TAT. We have 4 AXD. And then second is KAC. Fine. Now read this table column wise. For ciphertext, this column will be XW, AXA, then ANTD, C. Then you have TXTAK. So that means these letters are arranged in in a way that hacker will definitely take time to get the actual plain text. So this is a ciphertext equivalent of the given plain text. Attack X at X dawn when you are substituting X again. So this would be a equivalent cipher text. Then steganography is something. Steganography. It is an art of hiding messages behind pictures. It is art of hiding messages behind pictures. That is called steganography. Here some message is made, then the message is covered with the picture and that picture is sent. Then suppose this is a message, say hello. It is combined with picture 1.jpg. The foreground would be 1.jpg, whereas back text would be message sent over the communication channel or internet received by the receiver. So remove the picture and get the original text. This is called steganography. The person will be, the receiver will be able to remove the picture and will be able to read the text which is behind the picture. This is called steganography. Okay. See, besides the messages, you can even hide any audio clip, any video clip, text, or any image within an image. That is any kind of digital content can be inserted or can be hidden within a image, that is called called steganography, where you can hide any audio clip, video clip, text, or any image behind another image. That is called steganography. Fine. So next is very important algo, which is generally asked in the exams. That is DES, data encryption standard. It was formulated by NIST, formulated and proposed by NIST. This is an organization, NIST is an organization which usually deals with the security of the data which is being sent over the internet. Fine. So NIST is an organization which generally deals with the security of the data, which formulates the policies and the procedures which generally governs the communication of the data over the internet. Fine. So this is the organization. So what are the features of DES? So first feature is it is a block cipher. Second, it is a symmetric cipher. Third, okay. So first of all, earlier what we did was stream ciphers. That is Playfair, Hill cipher, rail fence, any cipher you have done, either you have done the substitution cipher or the classic encryption technique, they were all stream ciphers because they were working on a bit stream. Fine, stream of bits it is working on. Suppose you were saying attack postponed till 2 a.m. in the morning. Fine, so that means that particular line is a stream of bits. So that is particularly a stream cipher, which deals with only one line of plain text. They are known as stream cipher, where the data is flowing in the form of bits. That is called stream cipher. All the techniques which you have done earlier are the stream ciphers. Now, what we will be doing today is one of the best technique which was used in which was used by Germany during the World War I and World War II. So that was your DES, that is data encryption standard, and it is generally the block cipher. And block cipher means it will actually encrypt the 64 bits 64 bits of the plain text, not a single bit, but it will take a group of 64 bits, then convert it into the ciphertext. So if input is 64-bit plain text, then output will also be the 64-bit. That means a chunk of data is converted to the cipher, that is called block cipher. Then symmetric cipher means it uses same key for encryption as well as decryption. It uses same key for encryption as well as decryption. So that is called symmetric cipher, and that we have done already. When both sides, that is receiver and sender, uses the same key for encryption as well as decryption, that is called symmetric cipher. Now, it will take the input of 64-bit plain text. Input is 64-bit, output is 64-bit ciphertext, and it uses the plain, the same key for encrypting as well as decrypting. Now, for encryption, to make it highly secure, it uses 16 rounds of encryption. It follows 16 round of encryption where each round is called fiscal round. I'll explain what is fiscal round. As we proceed with the algorithm, I'll show you what is fiscal round. So 16 rounds of encryption is done where each round is called fiscal round. Fine. So these are the four features of data encryption standard. First feature is it is a block cipher. It converts the chunk of data or a chunk of bits to the equivalent ciphertext. Then symmetric cipher, it uses the same key for encryption as well as decryption. Then it takes the input for 64-bit as the plain text. Then for encrypting the plain text into the corresponding ciphertext, it uses 16 rounds of encryption, where each round is called a fiscal round. Now, steps for the algorithm. This is a diagram for the DES. So the steps for DES, first of all, is initial permutation, in which the your numbers are being arranged. I mean, your bit is being rearranged. So, for example, you have ABC. So, in how many ways this can be arranged? In 6 ways. See, A, C, B. Then you have BAC, BCA. Then you have CBA. Then you have CAB. Right? So these are the multiple ways, 6 ways in which you can arrange these letters ABC. Similarly, when we are given a ciphertext, when we are given a 64-bit plain text, then we will perform the initial permutation so as to rearrange that 64 bits. Fine. So that initial permutation will be the rearrangement of 64-bit plain text, which is given as input. So this is rearrangement. I write it here only. Rearrangement of 64-bit text which is given as input. Its corresponding binary form will be given as the input. First of all, you will rearrange the plain text, then corresponding binary form will be given as the input for the initial permutation. Then, second step, 16 Feastal rounds are performed on the given plain text. So, we have round 1, round 2, round 16. These are 16 Feastal rounds. These are 16 Feastal rounds which are performed on the initial permutation. Now, we have the initial key, as I have told you, that 64-bit data will be converted to 64-bit ciphertext. Fine. For that, you have the key, initial key of 64-bit. Fine. Some processes will be done in order to convert this key into the 56 bits at the first stage. In the first stage, your 64-bit key will be converted to the 56-bit keys. Then this 56-bit key is converted into the 40. Some processes will be performed on the 56-bit key so as to convert it into the 48-bit key. Fine. So for every round, if there are 16 rounds, then it means we will have 16 different keys which will be applied on each round to get the corresponding ciphertext. 16 different keys of 48-bit will be applied to each round separately. See, for round 1, the key would be K1, for round 2, key would be K2, and for round 16, the key would be K16. And all the keys will be of 48-bit each. And all the keys will be of the 48-bit each, and they will be reduced from the initial 56-bit key which we have retrieved from the 64-bit key. First of all, we have the key of 64-bit, then we will convert it into 56-bit, then some processes will be performed to convert it to 48-bit. Then 16 rounds will have the application of this 48-bit key in each round separately so as to get the final permutation, and after the final permutation, or we will get the 64-bit cipher text. See, 16 Feastal rounds, then swapping of left and right parts. Actually, 64-bit bits will be divided into two halves of 32-bit, and then we will swap them left and right, and finally we will get that final permutation. Finally, we will get that final permutation. I repeat, first initial permutation in which the rearrangement of 64-bit plain text is done, then its corresponding binary form is passed to the Feastal rounds, where Feastal rounds will have the key of 48 bits, and every round will pass through this round. Every data will pass through this round 1, round 2 with the help of key, but with the 48-bit key. Actually, there will be some operations which will be performed in round 1 using the 48-bit key, then in round 2, then in round 3, and final output will be the, you will do the swapping of left and right parts, and then you will get the final output. And that would be 64-bit cipher text. And please do remember that in each round, a separate key will be there for separate key will be applied to each round. Of 48-bit will be applied to each round. A separate key of 48-bit will be applied to each round. Diagram for the fiscal round. This is round number 1, and similar kind of 16 rounds will be applied. See, first of all, 64-bit data is as input. The ES accepts the input of 64 bits. Then we divide this data into two parts, equivalent parts, that is of 32 bits each. One we have named as left 32 bits, another part we have named as right 32 bits. I repeat it again. 64-bit data is the input for the fiscal round. In the first fiscal round, it will accept the 64-bit of data. Then it is divided into two equivalent parts, that is of 32 bits each. Fine. So this is left 32 bit, this is right 32 bit. Fine. Then this is a function block. These right 32 bits are passed through this function block along with the key of 48 bit. This is first key, that is of K1, that is K1 is of 48-bit key, and this is applied along with these bits to the function block. I'll explain the function of a function block later on. So first fiscal round, you just understand what is fiscal round and what are the units which are used in it. Then we will do the each and every component of the DES. So first of all, 64-bit data is divided to left 32-bit and right 32-bit. Then this right 32-bit and 48-bit key, which we have reduced from 64-bit key initially, is applied to this function block. Now, whatsoever the output is of this function block, there will be the output of this function block. which is XORed with left 32 bit, which is XORed with left 32 bits. This output of the function block is XORed with the left 32 bits. Fine. And after the XORing, the new left output of this block will be the input for new write. The output of this XORing will be the input for new write. Fine. And these write 32 bits becomes the new left 32 bit directly. I explain once again. Write 32 bit and 48 bit key is applied to the function. Then this is XORed. Both of them are left 32 bit are XORed with the output of the function block. And finally, whatever the output, suppose this is output 1 and this is output 2. So output 2 will be after the XORing. After XOR, the output will be output 2. And this output 2 is the new write 32. It will be the new write 32 bit. Similarly, these write 232 bit will straight away become the new left 32 bit. Fine. Now this new write 32 bit will be applied to the function block with the key K2. So this is round 1, Feastal 1, round 1. Now this is Feastal round 2. New write 32 bit along with the key is applied to the function block, and the output of this is XORed with the left part, that is of 32 bit. Again, the output of this will be sent to new write, and the third Feastal block will be performed. This is how Feastal blocks works. This is how Feastal block works. Now let's do what is inside the function block. This 32-bit data was the write data, which was given as an input to the function block. So I'm taking it as right side data. Okay, for more clarity actually. So 48-bit was the key which was given to it. After that, XOR has to be performed. So this is what is inside the function block. I tell you. See, 32-bit needs to be expanded to 48-bit, fine, so that we can XOR 48-bit key data with 48-bit data. 32-bit data is converted to 48-bit data. And when this 32-bit data is converted to 48-bit data, it is called expansion. It is called expansion because you are expanding the data by how many bits? 16 bits. 32-bit data will be expanded to 48-bit data so that we can perform the XOR with the 48-bit key. Fine. And for that, we have these substitution boxes. S stands for substitution boxes. Substitution boxes. These are the boxes. These are the 8 boxes of 6-bit each. Substitution box. Substitution boxes, they are of 8 boxes, as you can see, S1, S2, S3, S4, 5, 6, 7, and one more, S8. So 8 boxes of 6-bit each. Finally, that 48-bit data is again, contracted to 32-bit data because we want the output as 32-bit. Fine. Now, what happens inside the expansion box? That is, I repeat again so that I can erase it, and I'll tell you. So this is 32-bit, which was the data from the right side. It needs to be expanded to 48 bits before performing the XOR with the 48-bit key. Once it is converted to 48-bit data, then the XOR will be performed with the 48-bit key. Fine. And final, the output will be in the S1, S2, S3. These are the expansion boxes which are responsible for expanding the input to the 48 bits. Fine. After that, once the expansion is done, we will convert the 48-bit data to 32-bit data, because if we have given the input 32-bit, the output should also be 32-bit. And the output of this left box is given to the permutation box, and you will get the 32-bit output. So we will see the functions in the subsequent sections of the lecture. So let's see what is inside this S boxes, that is substitution, or the expansion boxes. What happens inside it? Or substitution box. Fine. 32-bit data will be in form of 0 and 1. Zeros and ones. But for the better understanding, we are taking the text. So this is our text. Don't give money. Don't give the money. See, for example, the text is given to you as don't give the money to that person ever. Fine. So we have divided the text into blocks of 4 bits each. If I club S1, S2, S3, S4, S5, S6, S7, S8, this total becomes 32 bits. This is the input which we are receiving. You consider it as text, but normally system, as we know, our system accepts the zeros and ones. But for our simplicity, for sake of understanding, we have converted it into the text. Now, how this individual box will be converted to 6 bits each, because it is having 4 bit, and we have to convert it to 6 bit in order to get the total 48 bits. So let's take the example of S2. 1, 2, 3, 4. So write GIVE as it is. GIVE as it is. Take the last, last alphabet from the S1. Take the last allocation of the S1. So this is having T. Similarly, take the first alphabet from the box S3. So this will become T, give T. Fine. So this is expanded to 6 bits. Fine. Now take the them. T, H, E, M. Now, last alphabet of S2 is E and first alphabet of S4 is O. This is S3, this is S2 and it is expanded to 6 bits. Now, O, N, E, Y. Fine. First bit, last bit from S3 and first bit from S5. So this becomes MONEYT. ONEY as it is. Take the M from here and first bit from this, first alphabet from S5. So this becomes like this. Now let's do the first one. DONT. So you will take the first from this and last from this. Take the last from S8 where my text is terminating, that is at the S8 block. So take the last alphabet from the S8 block. Fine, this is how it is done. So this becomes 6 bit. Now let's do it for others also. Similarly, you can do it for others. So 2 TOTH. Take the first from A and last from Y. So you have taken in S5, Y is the last and A of S6. So this is how it is expanded. Now next, S4, S5. Let's do it for S6. So S6 will be A, T, P, E. Last alphabet from S5, that is H, and first alphabet from S7, that is R. Fine. So in this way we will move. And for S7, R, R, S, O, N. First alphabet from S8, E, and last alphabet from S7, S6, sorry. This is S7. So last from S6 and other from S8. Then now you will, what you will do, last from N and first from this, first from S1. So you will take D. So never D would be the S8. So that means you have, when you are going to club this, it will become 48 bit. The total will become 48 bit because it is being expanded. Okay. So this is being expanded from, in the expansion box, this text is being expanded from 32 bit to 48 bits. Fine. So this is your, expansion box, how the text of 32 bit is converted to 48 bit in a DES. This is a table for SBox 1. See, how many S boxes were there? 8. So S1, S2, S3, S4, S5, S6, S7, and S8. Now, what happened? 48-bit key was XORed with 48 bit of data. In step 1, we did that. First of all, what we did is 32-bit data was expanded to 48-bit. Then it was XORed. Then it was XORed with 48-bit key. Fine. Now that 48-bit data, after the XORing, the output is coming to these S boxes, and it is divided into 6 bits each. So every S box will have 6 inputs. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So these are the 6 inputs for each S box, substitution box. Now we need the output of 32-bit. So that means the output will be 30 and 4 bits each. The output of every S box will be 4 bit each. This is 4 bit. This is again 4 bit, and so on. Every 4 bit. And when we add these 8 into 4, when we multiply 8 into 4, 8 S boxes with 4 bits each, we will get 32 bit. Now, how to convert this 6 bit into 4 bits? For example, this is the data which is given to us. This is the, input which is of the S box 0, 0, 1, 0, 1, 1. Fine. So these two numbers, first, that is least most significant bit, and least significant bit and most significant bit, LSB and MSB. LSB and MSB. This is your LSB and this is your MSB. Least significant bit and MSB, that is most significant bit, makes the row. That is 0, 1. It is first row. And 0, 1, 0, 1 is 5, which says column 5. Okay. So for every S box, a table will be defined. A predefined table is there. This is for S box 1. So go to row number 1, go to column number 5. Go to row number 1 and column number 5. You will find the intersection of both is 7. You will have the intersection of both is 7. So 7 is equivalent to 0, 1, 1. That is the 4-bit output of S box. 4-bit output of S box. Fine. Similarly, when the input for the S2 is given, first, least significant bit and most significant bit becomes the row number, and the rest bits becomes the column number. So you get the intersection of the row and the column as a simple number, which was defined in the box and converted into the 4-bit output. So this is called, this is first S box output, and similarly you can find the output for all the 8 S boxes. Club them together, you will get the 32-bit output. You will get the 32-bit output. Okay. For S2 it might be different, for S3 it might be different, and so on. It might be different for S8 also. So you club all these 4 bits and get it as 32-bit output. Fine, which is given to the final permutation box. Okay, dear students, thank you for the patient listening and thank you for this lecture. If you have any doubts, you can WhatsApp me personally so that I can clear your doubts. And so now it's the poll time. So let's put the poll questions.